So here's the classical mechanics by hand. We looked at it a little bit in class, but here's going through it again in some detail. So as a review, position, or we tend to think of it as height right now, but you may also hear the term displacement. The derivative of height or displacement is velocity. So if I have a position versus time graph, then the derivative of it should be velocity. Nice time to practice units. The units of velocity, because it's a derivative, will be y's over x's. In this case, the unit of our y is kilometers. The unit of our x's is hours. So the units of velocity for this particular graph will happen to be kilometers over hours. This is also a good time to practice graphing a derivative. I have a graph that is linear and increasing. So from 0 to this point, we have positive derivatives. So when I draw the graph of the derivative, it has to be positive. Because this is a line, it will also be horizontal. So we'll have a horizontal line that's positive. After wherever this point is, about 0.25, the graph of the position starts decreasing. So our derivative will be negative. So we're now going to graph below the x-axis. It's also constant, so it'll do something like this. It's not the greatest, perhaps, useful graph, but you can practice those components. Hey, there's our graph. So now we've changed. We now have velocity versus time. And in fact, the derivative of this is then acceleration. So we could find the units of acceleration. Again, units are always the y's divided by x's. So our units would be kilometers per hour divided by hour, or if you prefer, that's kilometers per hour squared. Both are fine. And that will be our acceleration. That also means acceleration is the second derivative of position. That's what we're going to use to do things by hand. So the classical mechanics model says the only force contributing to acceleration is gravity, which is not always an appropriate assumption, but if it is, we can say that acceleration is either negative 9.8 meters per second squared or negative 32 feet per second squared, depending on your units. And that's it. There's no mass involved. There's nothing else involved. It's just gravity. And these numbers, 9.8, 32, those are numbers we know from experiments. All right, so how do we use that to look at this particular prep problem from day 27? That was our snow day. Well, we're given some information. We're assuming then that acceleration is equal only to gravity, and we're looking at meters. So I'm going to use that negative 9.8. Because we're using a model that makes that assumption, I can then integrate both sides of this equation to get to velocity. So as a reminder, acceleration is the derivative of velocity. So when I integrate a derivative, I get its antiderivative. So just velocity. Right? So integrating acceleration gets us to velocity. Negative 9.8 is a constant. So when we use the power rule, we get negative 9.8 times t, because dt tells me that's my variable, plus some constant. I can solve for that constant because we're given that the initial velocity is 7. So when t is 0, velocity is 7. And so we plug in 0 for time, we solve, we get that the constant is in fact 7. So the equation for the velocity is negative 9.8t plus 7. Cool. We have an equation for velocity. From here, we can actually find the equation for height or distance because velocity is the derivative of position. So we can use the same trick again. I'm going to integrate both sides of this equation. So velocity, the integral of velocity, is the integral of negative 9.8t plus 7 dt, right? We could do the same thing to both sides. The antiderivative of the derivative is the original function itself, so position. Right, negative 9.8t. T is still my variable because that's what dt tells me. I need to add 1 to the exponent of t and then divide by it. And 7, we have a constant, so we're going to add a t and then a constant. Furthermore, we know that when t is 0, s is 40. So I have 40 equals negative 4.90 squared plus 70 plus c. And so that'll tell me my constant is c. So the equation for s of t is then negative 4.9 t squared plus 7t plus 40. So that's how we can do by hand to get to both the position and the velocity under this model that the only thing affecting acceleration is gravity. The next slide is actually going to go through how do we solve the questions that were actually asked. So here are the two equations we found. We want to find maximum height. Maximum height occurs when the velocity is 0, because to reach a maximum height we have to have gone up and then come back down. So the velocity, the derivative, must in fact be 0 there. So I'm going to take my velocity function, set it equal to 0, and then solve for t. There's the written version has all of the steps. So I'm going to simply get to t equals about 0.71 seconds. Once we have that value, that's where the maximum height occurs. But we don't have the height. We have to put it into the position function to find out how high we are at that time. So negative 4.9 times 0.71 squared plus 7 times 0.71 plus 40. If you run through that, you get about 42.5 meters. The other question is, when does the object hit the ground and what is that velocity there? When does it hit the ground? Well, if an object hits the ground, that means it has hit a height of 0, right? We've hit the ground again. So I'm going to start by setting my position function equal to 0. So you can use several things. You could use the quadratic formula. You can plug things into an online solver. I don't really care in terms of solving this, but you should get 2 answers and you will get t equals 5/7, 1 minus the square root of 17, or t equals 5/7 times 1 plus the square root of 17. This first one here is negative, so we won't count it. We're going to assume you can't go backwards in time. So our only solution is this one, which is about 3.66 seconds. So we hit the ground a little before 4 seconds. We also want to then figure out what's the velocity then. So we're going to put that same time value into our velocity function. And you get that we are at about negative 28.9 meters per second, which is quite fast. So that's about 65 miles an hour. So this particular object hits very hard in the ground when it lands eventually.